All right, so we've just looked at the exam solution. Your next assignment is on Blackboard. I just loaded it before class. Homework 5 is related to hydrographs, and that's due on Monday the 19th of February. And then there's a handful of students in here who are in the Environmental Engineering 670 class, looking a little bit to the future. Their research project report is due on Monday, March 4th. But if you're not signed up for the graduate class, you don't have to worry about the research project. That's not a part of your course. I just wanted to mention it. Okay, we're going to be talking about basins and losses and rainfall excess, kind of defining some terms that are going to head us in the direction of how to translate rainfall amount to the runoff. Because if you think about what we've discussed so far, we've discussed the basics of precipitation, the basics of infiltration, the basics of evaporation, and the difference between those things is the water that runs off. So let's consider a watershed. Now, a watershed is defined by geographic boundaries. Here's a ridge line, and the watershed is an area where if rain occurs, all of the moisture is going to travel to a central outlet point from the watershed. So it's going to first flow over the surface as a sheet, and then once enough sheet flow comes together, it will experience what's called shallow concentrated flow. So it's not quite in a channel, but there's water moving over the surface at a faster speed than it would as if it was just flowing as a continuous sheet of the same depth. So it goes from sheet flow to shallow continuous. Eventually the water enters channels, and it's gradually flowing through streams that are getting increasingly larger. And the reason why the streams start off small and are getting bigger and bigger is because streams come together. There's more flow that's contributing the further downstream you get. So if I just pointed at a certain location on this map and I said right here, then it would be only a small area that contributes to flow at this point on the stream. But then if I point to this point on the stream, now look at all of the upstream area that's contributing to the flow at that location. So the further we go downstream, the larger the contributing area is. So a large-scale hydrologic model asks us to apply a volume balance to keep track of the inflows and the outflows. And in fluid mechanics, you were introduced to the idea, the Reynolds transport theorem, which says that there's inflow to some control volume, there's outflow from some control volume, and the difference between the two is whether the storage will rise or fall. So we can say is that accumulation is inflow minus outflow. So when there's capacity for storage, in doesn't equal out necessarily, but the accumulation equals the difference between the inflow and the outflow. So look at this watershed. There can be water coming into the watershed from two places. Water can come into the watershed as if there was like a stream or a pipe that was bringing water in from external. So Q in is just saying, let's say that there's some water from an upstream river that's entering the watershed. PR is the precipitation. That's the moisture that's falling from the sky, whether it be snow, hail, sleet, rainfall, or fog. Could be dew that's falling at night when it reaches the dew point. But there's precipitation that's coming over the surface of the watershed. And so those are both inflows. That's water coming into the watershed. And now, what accounts for the difference between the inflows and the flow that's coming out, like a stream flowing out, we'd have to account for evapotranspiration. That's the combined effect of evaporation, which is the loss of moisture from a free surface of water or the loss of moisture from soil, and transpiration, which is the loss of moisture from plants. So we combine those two together in a lot of cases and call it evapotranspiration. Groundwater recharge could either be positive or negative. If we have water percolating down during a wet period, We could, like, you can think of the soil beneath our watershed as a sponge. And if the sponge is dry, like if it's been a drought conditions and now it's raining, then the groundwater recharge is going to be a positive value, and it would reduce from the amount of water that we see coming out. But in dry periods, it could be that the groundwater is seeping into the stream. And you sometimes see that in the summer. It hasn't rained for weeks, but there will still be a little bit of water flowing through a stream. That's usually because groundwater is seeping into the stream. And so where it says here groundwater recharge is either plus or minus, you have to ask yourself, is the groundwater being recharged, or is water leaking from the soil into the stream? So it can go either way, but it is going to either contribute to outflow or reduce outflow, depending on whether it's positive or negative. The change in surface storage is talking about lakes, ponds, and the volume of water that is in the stream itself. And so if you have a pond that's being filled up, then that would reduce the amount of flow out that you see as a stream. So that would be a positive value for the surface water storage. But if you're draining a surface water reservoir, like they maybe do at Summersville Lake during the summertime, if there's a dry period, there's still water going out of the lake, then that's going to contribute to the outflow from the control volume. LQ, large quantity user consumption. There are sometimes industries like power generation, chemical plants that use water for cooling. There can also be water that's withdrawn from water that's withdrawn from streams to provide like residential water surface. You know, here in Huntington, there's a West Virginia America Water treatment plant just up the road from here. It's probably only about a mile away, maybe less, where they're drawing millions of gallons of water per day from the Ohio River. So that contributes to the amount of flow that goes out of a watershed. And then there's also agricultural uses. And here in the eastern part of the United States, that's not as much of a factor as it is in the western United States, where agricultural use of water often dwarfs every other use of it. In places like Colorado, Utah, Arizona, they use a lot of water for agriculture, and it's by far the largest use. So this is just an application of the volume balance approach, and it's really useful in understanding what we're doing next. We're trying to predict the flow rate that comes out of a watershed. And before we can predict the flow rate, we have to just know what's the amount of water. And then once we know the amount of water, we use certain techniques to translate it from a depth to a rate. Remember, the difference between depth and rate is depth would be like saying it rained 3 inches over the watershed in a 24-hour period. So if we just talk about the depth being 3 inches, then that's an amount that doesn't yet have any time component to it. But then if we say that that 3 inches of rainfall happened according to a type 2 distribution, remember the type 2 distribution is just a way of saying when did the rainfall occur. It's assigning an intensity to different parts of the day. And we'll do the same thing with hydrographs. Hydrographs, we need to have some sort of a way of translating a runoff depth to a runoff flow rate. So there are a few other things besides evaporation and infiltration that we haven't talked about that reduces the amount of precipitation that's available for rainfall excess. So this is a new term, I think, that I'm just introducing for the first time, rainfall excess. So rainfall excess is what's left over after all of the abstractions have been satisfied. All of the things that, you can think of it as like paying a tax. You know, you have to satisfy the infiltration of the soil. There's going to be some evaporation that occurs. But what are the other things that also are going to reduce how much of the precipitation actually runs off? The two pictures here give you a hint of some of the other things that have to be satisfied that are abstractions. So abstraction as a term means that we want to translate the quantity or timing of rainfall into the amount that actually is being discharged from a watershed. And so we have to take into account the delay that can occur when water moves over the surface. So you can see that this is like a smooth tile on the one hand and a rough pavement on the other. So when rain falls on these surfaces, some of the rain that falls is going to be bound to the surface, and it's not actually going to flow. Because even if we had a slope on this pavement, if there was 100 millimeters of water that falls onto the pavement, a certain amount of it is going to stay on the surface and satisfy surface wetting before the rest of it flows off the surface. So the importance of that, of knowing the abstractions, is that it can reduce the intensity of the storm because of the delay, and it can have an effect on how big a pond needs to be, because ponds that receive runoff are sized partly by the runoff intensity that happens. And so these abstractions are going to be changing the time to peak for a rainfall into a time to peak for the runoff. And so all of the structures that we want to design, whether it's a channel or a pond or treatment processes that are having to be put in place to improve the quality of water before it's discharged to a stream, all of these are affected by things that reduce the intensity of the runoff. So here's an example of a type of abstraction known as interception. Interception can happen in urban areas and also in rural areas. So you can see here's a series of high-rise towers, and when precipitation comes in at an angle, then we have to wet the surface of those towers before additional precipitation makes it to the ground. So it will cast a shadow on the leeward side of these towers. There's going to be a shadow that doesn't get wet. So a certain amount of the precipitation doesn't make it to the ground. A certain amount of the precipitation is going to be wetting the surface of the building. And it can be buildings like that are really tall. It could be small buildings, but this is just an example of an urban abstraction in the form of interception. Vegetation is also playing a role when it comes to interception. This is kind of a close-up shot. You can see a droplet of water that's been captured by a leaf. And so a certain amount of the rainfall that's falling from the sky won't make it to the ground. And if it doesn't make it to the ground, it's not going to run off. And think about, there's going to be multiple layers of leaves. If you look down from above, depending on what kind of vegetation there is. If you're in an arid area where there's not a lot of plant life, you could look down and see mostly dirt or mostly the ground surface. But then in a heavy canopy, like in a rainforest or even around here, if you're looking down from above, there could be multiple layers of leaves, so that each one of them has to be satisfied and wet before all the subsequent drops of water are able to get to the bottom of the ground surface. So here's a picture of my driveway. This is what it looks like these days. You know, during the winter when there's not a lot of vegetation, then the interception would be pretty modest. But then during the summer, that same area is almost impenetrable. The raindrops that are falling downward, if you stood under the tree, you could be under there for 10, 15 minutes, depending on the nature of the storm. You could be under there for a good long while before you get wet. So I'm going to show you a table here in a minute, but keep in mind that not all vegetation is the same. And the amount of interception doesn't just depend on the type of vegetation. One of the research projects I've done in previous years is looking at how seasonal variations affect the amount of precipitation that actually contributes to flash flooding. And I put some stream gauges into a watershed and compared it to precipitation data that I gathered. And so this is some data that I generated a few years ago looking at, in December, a storm that occurred. And comparing some rain gauges that were in a completely open area to rain gauges that were underneath trees. And in December, there was just a bunch of sticks above the rain gauges. There weren't any leaves on the tree at that point. There had been some heavy windstorms, so all the leaves were off, and it was just the small amount of interception that's caused by branches up in the sky. So there was a little bit of a reduction. If you compare the rainfall that was measured under the tree compared to the open area, the amount was reduced by 9%, and there was a delay for when you got to a certain amount. So this delay is almost as significant as the reduction in amount, because you'll learn more about the idea of routing. Routing a storm means the time delay that occurs between when a storm begins and when you actually start to see the flow at the outlet. So this was during December when there wasn't much vegetation on the trees, and then in June the canopy was completely leafed out, and the reduction in precipitation amount went from 9% in December to 32% reduction in the rainfall depth. So you can see there's a big effect, a big improvement in interception when there's leaves on the trees, and the delay was lengthened as well. So it was interesting to see that this is more than just theoretical. You know, this effect can be observed in our area with pretty simple rain gauges. So this is the table I was mentioning before, and this shows different species of trees and their typical interception percentages as this is being reported. You'll notice that there's a variety of references, and so sometimes the same type of tree has been measured with different values, and that could be related to geography. And keep in mind that all trees aren't the same height. So you can have mixed eucalyptus trees that are 100 feet tall, and they'd have a certain amount of interception that's different from a eucalyptus tree that's 50 feet tall. So the maturity of the stand of trees is going to play an effect, but these are typical values that you could be expecting to see. But what this method doesn't say, this is just a percent interception. It's not saying what kind of a storm was used to generate this data. And so you could have 100% interception for a very small storm. And you maybe have seen this or experienced it. If you go out under a tree and it's just a passing storm that passes through relatively quickly and there's not a lot of depth, it may not fully penetrate the tree at all, so that it could be completely dry under the tree. But a heavy storm could overwhelm the tree much more quickly. So there are actual effects that this table doesn't take into account, like the characteristics of the storm, local climate conditions, such as the humidity and the rate of evaporation, density of vegetation, the quality of the vegetation. So rather than just applying a certain percentage like this, there's been a method proposed that's a little bit more sophisticated, that takes the species of tree into account, but also classifies the amount of evaporation that would occur during the event, and then also the intensity of the storm. So the amount of rainfall is going to play a role on how much water is actually intercepted. So this is an improved approach where you're starting off with some storage depth. You could think of this storage amount as the maximum amount of precipitation that could be stored by a tree of a certain type. But it also goes one further, and it applies a leaf area index to say how much of the evaporation is going to occur during a storm. So let's just to try out how this equation works, consider the following example. Let's say that we had a storm that's 1.5 hours long, has a depth of 3.8 centimeters, and then it's measured that the evaporation during the storm is 0.3 millimeters per hour. So that's the evaporation at ground level, but there's going to be multiple layers of leaves that are having evaporation. So we apply the leaf area index of 6.5 to that. So here in this equation, K, it's not hydraulic conductivity like we've seen that variable used for soil properties. The K here is like how many layers of trees are there between the sky and the ground. So in this example, a leaf area index of 6.5 is basically saying that you've got a tree, but from the air down to the surface, there would be 6.5 on average interceptions, or it could be like 6.5 layers over which the evaporation is occurring. So let me pause for a second, see if you just get a feel for how to put this into the equation. Remember that we have to have consistent units. So look at the storage is in millimeters, and the precipitation that I've said here is in centimeters. So since it's going to be a ratio, you need to have it be in the same units to be able to put it into the exponential function. All right, so it's 38 millimeters of precipitation as the P, and then the storage for this particular spruce trees, we're going to use 7 millimeters as the S value for the storage. And so the storage is mostly fully saturated in the case of 38 millimeters of precipitation. Of that 7 millimeters of maximum potential storage, we've got 6.97. So we're getting almost all of the storage potential. And then the evaporation that's occurring, there's 2.9 millimeters of evaporation that happens during the storm. So the runoff and infiltration amount, that's the rainfall excess that actually, the amount of precipitation that makes it to the soil surface is 28.11 millimeters. So, about a third of the, maybe a little bit more than a third of the precipitation is being intercepted by the tree in this case. And this is a little bit simplistic because what you know already is that evaporation is dependent on the humidity. And it's not always the case that humidity is 100% as it's raining. It can rain in arid areas and still have the humidity below saturation. So, it's not impossible that there's going to be evaporation during a storm, but it's something that we need to be careful to try and calculate accurately because it's going to completely, affect the amount of interception that occurs. And so in order for water to flow over the surface, it first of all has to make it past the trees or the buildings. Depression storage is another category of abstraction where water's not going to begin to flow out of a watershed until all of the little puddles are filled. And if you think about the parking lot that's here to the side of our building, the same is true with that in an urban environment or in a rural environment. All of the small depressions have to be filled up before water is going to be flowing over the surface. So this is just showing like a puddle in a field, and water would maybe be flowing towards it, but it's not going to flow out of this depression until it's all the way full. So it's kind of like a small reservoir. Water also wets the surface of pavements, and this is showing a runway. Runways are someplace where they really are careful to make sure that the water doesn't get too deep, because I'm sure you've heard of the phenomenon of hydroplaning, where as you're driving a car, if the water is too deep, your car can actually get on top of the water and you'll lose control of the vehicle. You're losing traction if you're up on top of the water rather than if your tire's pushing the water out of the way. So if you have a moderately flat surface, then the amount of water you need to plan for allocating and overcoming the depression storage is about 0.5 millimeter. if that's a steep surface that's going to be draining more aggressively, then it would be less depression storage than flat surfaces. You can see that the more vegetated a surface is, the higher the depression storage would be. So like a lawn is going to have more depression storage than pavement. So pavement, there's only a certain amount of wetting that has to occur before the water can flow over the surface there. But there's more specific surface area for grass, where in 1 square meter plan view of grass, there is going to be more than a meter of surface area because of all of the blades of grass that are growing up out of it. And forest litter is what you have after multiple seasons of trees that have leaves falling down and twigs that are breaking off. If you walk around in the woods, you'll notice that it's not just dirt that is on the ground. It's mostly leaves and organic material on the ground. And there's quite a bit of storage in that forest litter because as organic material, it has lots of layers to it, and it slows down the movement of water considerably. So it's an important factor to keep in mind when you're finding out how much water is actually going to come out of a watershed, is the type of surfaces that's there and whether it's going to hold on to water before flow occurs. So steep slopes tend to have higher water velocities and lower storage quantities than flat slopes. And the affinity of the material for water, like decomposing organic material, would have a high affinity for water and would absorb it and bind to it, compared to inorganic surfaces like concrete and asphalt. And then you always have to keep the antecedent moisture condition in mind and whether it's been raining recently, because it could be that the depression storage is already fully saturated, and so the next subsequent storm that comes along, it's not that every storm is necessarily going to experience the same amount of depression storage if in previous days there's already been moisture that's overcoming this needed abstraction. All right, well, that's it for today. So what we'll do on Friday is continue talking about hydrographs, and then I'll get back to you about the exam thing and the evaporation. So if you have any other questions on your test paper, then feel free to stop by during my office hours, and I'd be glad to go over it with you.
We'll send you an email today with the topic.
Okay, great.
Yeah, but I think it will be the